Welcome to the Math Record. Today I'll be covering Newton's law of cooling and logistic functions. Let's start with Newton's law of cooling. So basically, Isaac Newton said that an object's temperature changes at a rate proportional to the difference between its own temperature and the temperature of its environment. So to understand this as an equation, let's first define our variables. Let's say y is the temperature of your object, and let's say capital T is the temperature of the environment. Okay. So Newton's law of cooling says the rate at which the temperature of the object is changing, so dy over dt, lowercase t stands for time, so don't confuse these two, is proportional, so some value k, to the difference between the temperature of the object and the temperature of the environment. So we have the rate formula, but we want the original formula. So if we want to find temperature or y value, so basically what we could do is that we could move these y variable equation to this side and dt to this side and then integrate. So that would be the integral of 1 over y minus t dy is equal to k dt. So all I did was just move this here, move this one here, and then integral. Sorry, I forgot the integral here. So the integral of this would just be the natural log of y minus t, add some constant, let's say c sub 1. Integral of this is kt, because we're doing respect to t, and this is a constant, and some c sub 2. Now c sub 2 minus c sub 1 is c sub 3, because a constant minus constant is just some kind of constant. Now if we want to find c sub 3, we need to make this 0. That means we make t equals 0. So when t equals 0, that means the temperature at t equals 0 means that we're looking for the initial temperature of the object. So we write that as y naught. Okay, so that would be y naught, natural log of y naught minus t is equal to c sub 3. So we could substitute that back into our equation instead of using c sub 3. So natural log of y minus t is equal to kt plus natural log of y naught minus t. Or we don't want to work with natural log, so let's raise them both to a power of e. E to the natural log cancel each other out, so that's just y minus t. E to the natural log of e to the power of kt times e to the power of natural log of y minus t. That's just y naught minus t. And then we could just move t to this side, so we isolate our y. So y is equal to, make this a little bit nicer, y naught minus t times your e to kt, and then plus your t. And that is the original equation of our Newton's law of cooling. So to understand this, let's try an example. Let's say we have a cup of coffee, and it's initially at 80 degrees Celsius, and the air, which is the environment around it, is 20 degrees Celsius. And let's say in 5 minutes, it became 50 degrees Celsius. So what is the temperature of the cup of coffee in 10 minutes? And what is the rate at which the temperature is changing at that point? So first we want to find the temperature. So we need to find this. So we know y is equal to y naught, which is 80, minus t, which is 20, so that's 60. E to the power of k, we don't know what k is yet, so we need to solve for that. And our t plus plus the temperature of our environment, which is 20. We know in 5 minutes it became 50 degrees. So 5 times k. So 50 minus 20 is 30. 30 divided by 60 is 1/2, is equal to e to the power of 5k. So that means if we want to find k, we use our calculator, which is take the natural log of 1/2 and then divide by 5, which should come out as negative 0.139 approximately. Substituting that back into our equation, y equals 60 e to the power of negative 0.139 t plus 20. So in 10 minutes, we could plug in t equals 10, and we should come out using our calculator as about 35 degrees Celsius. Now, if we want to find the rate, we use this formula. So we know K is negative 0.139. We know the temperature at that point is 35, as we just calculated, and the temperature of the environment is 20. So that's negative 0.139 times 35 minus 20, which is 15, and you should come out as something at around negative 2 degrees Celsius per minute. That means the temperature that the coffee is changing at 10 minutes, the rate at which it's changing at that point, is negative 2 degrees Celsius per minute. Okay, now let's work with logistic functions. So basically, these are graphs that look like this, which kind of like are usually used to cover population growth. So to find this, it has really similar to Newton's law of Cooling's rate of change. Instead, it's dy over dt is now equal to k times y times m minus y. Okay, so we're doing the same thing. We put 1 over ym minus y. So we move this equation this side and dt to that side equal to, we have k left over, dt, forgot our dy, equals k dt. So I noticed that there's a negative y here, which we're doing with respect to y. I hate working with negatives, so what I usually like to do is multiply negatives to each side. So this negative goes to here, and that makes this a negative m, make this a positive y. So overall, when we integrate both of these, I can split this up because there's two equations on the bottom. I can split it as partial fractions. And the other one is y minus m. And that's the integral. And the integral of negative k in respect to t, that's a constant, so we make it linear. And let's call that c sub 1. And now we need to find the coefficients for these two. So basically, using the same technique, the cover-up method, as we did in partial fractions, basically we find out what makes 0 on the bottom. So in this case, y equals 0. Cover the y here, plug in 0. 1 divided by negative m plus 0 is 1 over negative m, or negative 1m. Now for this case, we need to plug in y equals m to make m minus m is 0. Cover that up on this equation. Got to get rid of that. Okay. Cover this equation. Plug in m, so that's just 1 over m. Okay, so these are just constants, so we can move that outside. So that means the numerator is now 1. Move this one outside. Numerator is now 1. So when we integrate this, this is just a regular reciprocal, so the integral is natural log. And 1 over m. The integral of this is the same thing as that instead of y is y minus m. So natural log of y minus m. And then as usual, we add a constant, so c sub 2. But as we did before, c sub 1 minus c sub 2 is c sub 3. So negative kt plus c sub 3. Okay. Let's delete a bit of this so then I can have more room to do the math. Now, let's multiply by m on both sides so we cancel out these 1 over m's. So that will be negative natural log of 1 over y plus natural log of y minus m. Multiply by m, negative m kt. M is just a constant times another c3, which is a constant, makes another constant, so c sub 4 plus c sub 4. Okay, so this is negative, so let's move that to the other side. So that's natural log of y minus m is equal to negative m kt plus c sub 4 plus natural log of y. So as usual, we're working with natural log. We don't want to do that, so raise that to a power of e. So e to natural log cancel each other out. That's y minus m. E to natural log of negative m kt. E to e to the power of c sub 4. There, so e, which is a power, goes to some, which is number power, goes to some number, means it's just another constant, so c sub 5. And e to the power of natural log of y is just y. So we have a y variable, so let's put them together. So move this to this side, so 1 minus e to the power of negative, e to the power negative mkt times c sub 5, and we have our y's, and then move negative m to this side, so this becomes m. So overall, we can isolate our y, and that becomes m divided by 1 minus, let's just move c sub 5 in front so it looks a little bit nicer, e to the power negative mkt. And we could substitute c sub 5 with like a different variable. So let's just say negative c sub 5 is b, so that's 1 plus b e to the power of negative mkt, so it looks a little bit nicer. And as usual, if you ever search the formula up for a logistic in Google, basically you'll get a formula that looks like this. And the top one would be called the carrying capacity. And that's basically it. And overall, this would be your original formula, and this would be your rate formula. Well, thanks for watching, and in the next video, I'll be covering, what would I be covering again? I will be covering arc length. We'll see you then.